I could do direct air capture, right? This is what everybody says is crazy because it takes so much energy. How about if I just plant trees? Wouldn't that be good enough? Let's just plant a lot of trees. Okay? Or I could use trees to make energy, and in burning the trees, rather than let the smoke go into the air, I pump the CO2 underground. This is so-called BECCS, biomass energy with carbon capture and storage. So I'm growing trees, cutting them down, burning them for your power plant, but the CO2 goes underground. It's called BECCS. All the people who are really keen on this are really featuring BECCS. So we enhance the natural uptakes one way or another, or remove it directly from air with our clever chemistry and chemical engineering. It will take decades to affect the climate because these are slow processes. Okay, how about enhancing the natural uptake? So here's a complicated slide which again shows the rates. These arrows show the rates at which things are moving. So here is fossil fuel and land use changes dumping CO2 into the atmosphere. 9 petagrams per year. And then here you have the CO2 coming down and going into the ocean or being taken up by trees that are growing. And so 5 petagrams per year are absorbed by the land and the ocean biosphere. So let's change the land management. Let's accelerate the weathering, fertilize the oceans. And so we have these 4 ways to suck carbon out of thin air. I mentioned one of these already, bioenergy with CCS. That's one way. We could grow more trees, so-called afforestation. We can capture directly from the air, or we can enhance the weathering. So these are the 4 schemes that we need to consider when moving forward in this review. So let's talk about afforestation. That is to say, I want to plant trees where forest does not exist. And the trees and vegetation consume carbon dioxide. They grow. It's totally passive. It's easy. It's expensive. All it requires is a lot of land that's not being used by something else. And maybe, if you don't do it correctly, the land that you do use now has to have fertilizers and water, because not all trees grow everywhere well, or for that matter, grasses. The idea, though, is that it's nice and passive because everybody loves trees. I know Vice Chancellor Brar loves trees, and so your campus is therefore so beautiful. So, happy Earth Day, let's plant a tree. But there's some issues with that. Okay, so if you do that, our current emissions estimate predict that about a gigaton of carbon could be accounted for if we plant more trees. We could remove 3 gigatons from the atmosphere through net growth and absorbing most of that from fossil fuel burning and deforestation. Exactly so. It's not like we can grow just anything. It has to be engineered. Yeah. Right? That's the word I like to use.
Trees like Ficus religiosa and Ficus belengensis have capacity to assimilate carbon dioxide more than any other tree.
Yeah, miscanthus in particular.
Strategies. And I think plants which bear oil and carbohydrates are more beneficial than any other, because carbohydrate has C6H12O6. They can convert 1 carbon into 6 carbon, and this way we can sequester carbon dioxide more easily than any other strategy.
Yeah.
Oils at the same time are high carbon compounds.
And these are all strategies that people are thinking about, and
yes.
They're all
Parking areas should not be inside the institute.
Sorry?
Parkings of automobiles and
yes.
It should be outside the campus.
Outside.
So the content of particulate matter inside the air is inside the campus is high as compared to the other side.
Yeah. So there are advantages to engineering the trees for the purposes of the regional environment, which is exactly correct. We do have to be a little bit careful, though, okay? Because ultimately trees die. And when they die, the microbes get them, And that ultimately it comes back into the air. Growing a lot of trees works for a decade or 2 or 3 or 4, depending on the tree. But unless you do something with the trees, sooner or later, the CO2 will come back. Okay? So we all just want to make sure we understand that. The agriculture sector in the world could be carbon neutral if these practices were widely adopted. That is, the management in terms of not in producing the highest crop yield, but in terms of producing the least CO2. And it's estimated that the air would be lowered by 40 to 70 ppm, and that's possible by the end of this century if we deploy all these techniques. Professor Reimer is frustrated again by his electromechanical devices. I've already gone through 6 batteries in my laser pointer, and I'm really quite annoyed. I must have bought cheap batteries. Speaking of not sustainable lifestyles. We'll keep trying. Yes, suboptimal. You notice Professor Blumik and other colleagues are not using laser pointers, they're using the pointers on their screen. That's because they're better than I am. Okay, so let's move forward. So what's one way around this problem of having the CO2 escape? And this is bioenergy combined with carbon capture and storage, BECCS. And this is the process by which that many people think is the most effective, and it's a very growing research community. And the idea is really relatively simple. You grow trees or miscanthus or other kinds of plants, and you burn them, and then you take the CO2 from that combustion process, capture it with the technologies we've been talking about, membranes, adsorption, absorption, and then put it underground. And so what you're doing is taking CO2 out of the air and putting it underground. It takes a decade time scales to have an effect, but nevertheless, you could produce power in a way that's carbon neutral or even carbon negative. So these technologies are known to exist. That is, we've been burning wood for a long time to generate power, and we certainly know how, in principle, to do the carbon capture and sequestration. The problem, of course, is you have to look at the land area. And as your colleague over here pointed out, not every tree is the same, and the amount of area you need is enormous. So if you make a bad choice for the kind of tree, you could wind up having half the country of India growing grasses just to sequester the CO2 necessary to have an impact. And that's certainly not something that your country, and for that matter, mine, can afford to do. The process is really quite simple. In typical fossil fuel burning, of course, you just take CO2 out of the ground and carbon and put it into the air. There are strategies for minimizing that effect, but biomass really gets around this with the net zero emissions. And then if you add the carbon capture, then you have a net negative emissions. And by the way, the energy that's produced from the biomass can be used, and we're going to say more about this in a minute, to produce biofuels. So liquid fuels, gas fuels, all kinds of chemicals can be produced from biomass. So there's a significant amount of our scholarly communities that are focused on taking cellulose and wood and grass and taking it all the way to the fine chemicals that are used, that are currently made from taking oil out of the ground. So that's another opportunity and another reason why BECCS is a particularly interesting process. It's already displayed. The technology is already known. This is a picture from a plant run by the Arthur Daniel Midlands and Schlumberger, two huge agribusiness companies. Here's a little picture of the United States in Illinois, Indiana, Kentucky. And they take corn and convert it to ethanol. The ethanol market in the United States is driven artificially high by its inclusion in transportation fuels. They capture a megaton per year of CO2. They transport it to a sandstone formation, and they're pumping CO2 underground. So BECCS can happen. It works. And here's a demonstration plant. Although taking corn to ethanol turns out to be not a sustainable way to produce energy, but nevertheless, the plant is well demonstrated. Another possibility is to take biomass directly to fuels. And so we might grow miscanthus, which takes up CO2. We have cellulosic biomass. It undergoes some kind of treatment. Enzymes digest it. We produce sugars. The sugars are used to grow microbes. the microbes produce, for example, butanol. Butanol is then a very effective fuel. Okay? So that whole strategy looks particularly good. Unfortunately, this requires a huge amount of energy to break up biomass, and that's sort of problematic. And if you look at this from the point of view of ethanol production, so here you have the input, miscanthus is... It's okay? Okay, yeah. Forest residues, wood chips, and so forth. There's the treatment. There's a hydrolysis. You get the sugar, conduct fermentation, do distillation, dry it, and you produce your ethanol. And there are sugarcane, corn, and cellulose are the possible resources. So that's a possibility. It looks like a way to introduce fuels. But let's take a look at how much energy is used. This is a particularly interesting paper from the Climate Intervention in the National Academy Press. It's for free. You can get it on the internet. And then Sally Benson, my colleague at Stanford, wrote an editorial about this, calling attention to the fact that if you look at the various steps along the way, CO2 comes in to grow the switchgrass, but the farm takes a little bit of energy. And then you have to transport it to the plant, and that takes a little bit of energy, and you lose some of the biomass, milling it down to the point where it can be fed, and then processed, in which you use a lot of energy. And then, the capture isn't perfect. And you reach the end and you realize that the CO2 actually, about half to 1 gigaton of biomass is needed to capture a gigaton of CO2. And so that's harsh. That's a harsh energetic process. And so researchers in our communities are looking at these at every step of the way, and in particular a lot of enzyme engineering and other technologies, ionic liquids and so forth, to try and minimize these losses in energy. How about how much biomass is available in order for us to conduct this? So here's the price in US dollars and the quantity of biomass available. And you can see the biomass can provide, if you add all these numbers up here in this graph, 2,000 petajoules of energy in 2030, which is really quite substantial. And you can look at the quantity available and look at their various feedstock types and recognize that we have an extraordinary amount of waste that we currently don't use, that we could use. There are dedicated feedstocks, but they start to cost money. And so then the cost of carbon capture becomes a little, or carbon sequestration from the atmosphere gets a little bit higher. The land mass use is particularly problematic because not every place is suitable for growing the crops we need to make fuels. So here's an International Panel for Climate Change projection. This is to achieve the Paris goal, which we started off with the very first lecture in the class. That is to keep below 2 degrees C. So this is the amount of atmospheric CO2 that has to be removed by 2100. And then you look at the various attributes. Let's just take abandoned land, the land around Amritsar that's what had something on it but is now abandoned. Let's take some of the forests and convert them into cropland and so forth. And you recognize that pretty quickly we run into the situation where we can't achieve the Paris goals because we don't have enough resources in terms of land. So the future is not completely clear as to how to implement this. And the best predictions I've read is that locally there are some places, some regions, perhaps in India and other countries, where this makes a lot of sense because locally there are resources and land available to do bioenergy. So in summary, for BECCS, about 7 to 9% of our electricity demand could be made this way. It's a significant reduction of CO2 emissions. Really the value lies in the sequestration of carbon from biomass rather than electricity. We could convert to liquid fuels. That also reduces the impact in the industrial sector. We create nice forests or regions if we engineer this properly. And there are certainly societal benefits to having a lot of trees around. Here's the kicker though. We need land, we need water, and in some cases fertilizer. And there could be significant damage to an ecosystem if we replace a natural and, quote, unproductive ecosystem with something that's completely engineered for our purposes. And this is a greater philosophical question about what value land has and what roles we want to play as humans in engineering the land to make our lives better. It turns out in the United States, 6% of the land area would be required to capture 1 billion tons of CO2, or 1/30th of the world production. This may not look like a big number to you, but I tell you, let's go to India. Let me just say to the leaders of India, would you please give me 6% of the land for this particular process? And I have a feeling it would be challenging politically. There is another option with biomass that's really quite interesting, and it's this notion of biochar. Biochar is an interesting aspect. So what happens if you heat up biomass, like wood or other products, in the absence of oxygen? Okay? So what happens is you're really accelerating in real time the formation of coal, because that's what happens with coal. These plant masses go underground, and in the absence of oxygen under high pressure and temperature, it converts to carbon. We can do that naturally, and all we have to do is what's called pyrolysis, which is to say you heat plants and matter up in the absence of oxygen. And from that, you can produce oils which can run our machines, and you can also produce biochar, or carbon, and the carbon can be adapted and planted in our farms to help increase the productivity of the soil, but it is stored forever because you've just made coal out of the atmospheric CO2 used to grow. So up to half the carbon would be sequestered if we went into the biochar business. So here's a picture of what that would look like. You use manure, compost, organic, grasses, anything you can grow. You conduct this pyrolysis. You generate some fuels. You also get some carbon back, which has a little bit of impurities, and that's returned back to the soil. So that's a process. Biochar is a process by which we could certainly pull CO2. It does, however, require high temperature and no oxygen. So that's an environment that's energy intensive. How do you get rid of the oxygen and do this process? And we've already seen for pre-combustion carbon capture that removing oxygen from air to produce pure nitrogen is a little problematic, although we can do it with membranes now much more effectively. So let's take a look at the CO2 removal in terms of gigatons per year and look at the estimates from the International Panel on Climate Change, where we are today, what could happen by the end of the century with changing how we grow our forests, burying biomass. So one way, by the way, if we grow a lot of trees and we don't want the trees to decay and release CO2 in the atmosphere, is you bury the trees. Grow a lot of trees, take them to the middle of the ocean, dump them in the ocean, they go to the bottom, they'll stay there for centuries. Here's our BECS, and here is where you add them all together. Here's, of course, biochar. So the net picture here is that in terms of removing, remember our goal here is not carbon capture and sequestration from coal-fired power plants. Our goal here is to decrease the amount of carbon in the air, to decarbonize the atmosphere, carbon which was put there in the first place because we're using the atmosphere as our waste dump for excess carbon. So that looks like a pretty powerful thing. So burying or burning is sort of a policy issue that has to happen probably locally or regionally. So let's get to the last topic. Not really last, but the topic I want to talk about next, which is direct air capture. And this is a highly engineered process whereby you imagine enormous arrays in which air is pulled with a fan across an active medium, an adsorbent, for example, and CO2 is captured directly from the air. And then with the use of a carbonate solution, potassium carbonate, for example, you can pull the CO2 and make it into minerals. So it takes CO2 from everywhere. The advantage of direct air capture, it's completely indiscriminate as to where the CO2 came from because it's in our air. Okay? No politics involved. Low land use, right? And can be scaled to fit wherever the local opportunities are. It doesn't work yet. That's the problem. And certainly not available on a commercial scale. And I want to call your attention to the fact that why we didn't really think about this as feasible in the first place. So you're going to have these enormous things that are going to be capturing CO2 from the air. The surface area is really quite excessive. So, but in principle, they could be built anytime, anywhere. In this lovely cartoon, you have cows on the farm and these gigantic devices which are capturing CO2. The idea is simple. As I mentioned before, you capture air. Air flows through. You take a CO2-rich solution of carbonate, which is in the device, and then you use a little energy to get the CO2 off. This is a stripper, if you like, and return the solution back again, and it runs continuously. It takes energy, and the source of the energy is important. Let's make a direct air capture system, and it's run from a coal-fired power plant. That's not a good idea, right? So the energy source has to be a renewable source, otherwise the whole purpose is defeated. Yeah? So that means it's ideal to place these kinds of devices where you have natural gas. Not so good, but wind, solar, nuclear, good ideas. Remember why I said it was a bad idea? If you look at what thermodynamics says about the minimum work necessary as a function of the mole fraction, remember we're down here, CO2 and air, and the energy penalty is the highest of all these other capture techniques. So energy is really problematic, and that's why when I first introduced this, I said only a crazy person would invest in this. But it turns out, this is 3 to 5 times as much energy. It turns out it may not even be carbon negative, because if you look at all the engineering, all the energy use that has to happen in this system, and in particularly the carbonate solutions that are recycled. So now you talked about absorption in these amine solutions as being slipping and so forth. These carbonate solutions require a huge amount of material. Nevertheless, it's compelling. And the reason we want to carbon capture carbon directly from the air is right now, Reimer has only been talking about capturing coal from CO2 from a coal-fired power plant here. But look at all these other sectors that aren't being affected by that. And so, like I said, the great thing is that it's completely indiscriminate. It could help with fugitive emissions from storage. That is, if we have a carbon direct air capture place near where there's a well or a site for geological sequestration, if there were a flatulence, a fart from the earth of CO2, then this could help with that. We don't have contaminants, at least not in high concentrations, so the chemistry of these direct air capture devices can be more straightforward. It's already available. Submarines currently operate with carbonate solutions to remove the CO2, as do spacecraft, so it's not a new technology. It's an insurance mechanism, right, where we might be able to deal with the rising climate. And so as a result, there are companies. Our students from Berkeley are getting hired by these companies. Many of them are startup companies, and Climeworks is one of them, in which they're building a plant in British Columbia. Here's another one called Carbon Engineering. This is their pilot scale, and this is their envisioned full-scale carbon capture, direct air capture devices. And if you look at the energy requirements, that's this column right here, you recognize they still vary all over the place, between 60 and 1,000 in these particular units, which is the dollars per ton of CO2 captured. So still a lot has yet to be known on these systems. So the direct air capture summary is that the point sources account for 1/3 of our fossil fuel. The direct air could address them all. It already works. We know it works. We know what technologies to utilize, and that's acid-base chemistry. The cost estimates vary a lot. So without a carbon price, it's probably not going to be feasible. And we could address leakage. Could be an insurance policy against low probability events. And whether it's carbon negative or not is maybe. And that depends on the source of energy from which you get this renewable source. So the next thing we need to consider is enhanced weathering. That's the last of our 4 steps to drag CO2 directly from the air. I'm going to try one more time with my batteries, because I'm getting very frustrated. So now I'm pulling old batteries up that have already been rejected because they weren't working. Everybody still with me? Yeah? Oh, that one works. Okay. Enhanced weathering. Remember that we have slightly acidic rain. It falls on silicate rocks and breaks down these carbonate solutions. It goes into the water and eventually winds up as limestone. And here's another. It could substantially remove CO2 in the air. We know it's part of the natural carbon cycle. We know it's been helping control the level of CO2 in the atmosphere for 1 million years. And so it's a very exciting opportunity. It requires an industrial scale of moving rocks around in a scale that's really quite unprecedented. And then, of course, crushing up rocks and distributing on 6% of the surface of the Earth has its own energy costs, which would generate CO2. And it has environmental costs, breathing particles. And so it could be quite high, but nevertheless, many people are talking about enhanced weathering. And the idea is really simple. Remember, we had this diagram which showed carbon dioxide, and carbonate. And the problem was the kinetics moving from this place to this place are really, really slow. So we really need to accelerate this process to form the carbonates. And this was the picture we had before, CO2 and water forming carbonic acid, which reacts with silicate rocks to get bicarbonate into the water and ultimately into the ocean. And we know the chemistry of that requires ions, and this is all review to you. It takes 10,000 years or more, and it's typically associated with about 1/10 of a gigaton of carbon per year. So enhanced weathering, let's take a look at the reactions you might imagine. Calcium carbonate, turns out in the long run it doesn't capture carbon. The olivines, like silicates, and these silicates have a net chemistry which winds up removing atmospheric CO2. So the idea is to start with silicate rocks, spread them on the ground, and have them capture CO2 and form these products. So we mine, crush, and apply silicate materials over the land surface, and they release cations during the dissolution, and this ultimately changes the pH locally, but nevertheless sequesters CO2. Carbon is transferred from the rock and atmosphere to the biosphere, and then ultimately to ocean. And so the kinds of scenarios you would imagine, we could reduce the CO2 concentrations by up to 300 ppm. So this is really the most significant of all the technologies we've talked about to bring us back into pre-industrial age. There are resources available, particularly if you go to places where you have a lot of water in the air, then there's less rock available. And there are a few drawbacks, yeah? So carbon is redistributed, so it's really not equivalent. It takes time, and the cost is comparable to direct carbon capture if you look at it on a cost of CO2 per ton, which means without a carbon price and a way to distribute the money from carbon taxes to the people that want to crush up rocks, it's not going to happen. So the net transfer happens from CO2 from the air to the carbonates. It's stored as a solid mineral. It could stimulate growth because some of these minerals are healthy. And it could mitigate ocean acidification because we're putting base into the water. Large capacity, very exciting capacity, unknown effects. We're talking about engineering rock and distributing on a scale that's never been done before, and it could be quite extensive. This will all cost energy, water, and large amounts of material. I need just a little sip of water here for a second. Turns out talking for 3 hours is harder than I thought. Good. Okay, can we fertilize the ocean? So that's another way to imagine decreasing carbon in the air. We put some minerals in the water, we grow algae, the algae take up CO2 and they die. And that's what's shown here. The oceans naturally absorb CO2. We add certain kinds of minerals and phytoplankton which bloom, consume the CO2 and drop to the bottom. It's really a compelling idea. People like this idea because it's natural, yeah? Because we're just exploiting known algae. If you calculate the scales on which this could be done, at most we could drop down the atmospheric concentration of CO2 by 40 ppm. Enormous damage to local ecosystems. If you imagine going to a place, off the shore of India and now seeding that place with enormous quantities of minerals, which bloom these phytoplankton, any fish and other natural species in that area could be seriously damaged. So nobody really takes it seriously, but the real reason has to do with pumping gas, pumping fluid. If you look at these circulation patterns for CO2,